Welcome to everybody. I'm Cristiano. I'm the lead AI scientist at PySchool, and this is our Spotlight Talk series. It's a series about, let's say, PySchool of AI alumni success stories. And today we are happy to host Johanna. She's a data scientist at Aurora Tech, where she applies AI and thermal infrared data to address environmental challenges, particularly wildfire detection and risk prediction. In 2023, she was a fellow at the PySchool of AI and gained experience in explainable AI by participating in a challenge that was about wildfire forecasting using explainable AI. And this was done with the National Observatory of Athens, which is a research center in Earth observation in Greece. In today's talk, she will explore how Aurora Tech forests, which are satellites from Aurora Tech, are using machine learning to detect wildfire from space, providing early warning and that are critical for rapid response. So this is what the talk will be about. And beside the talk, I just want to remind you to follow PySchool social media to be updated on our project, activity, events, talks, and whatever. So welcome again, Johanna, and I think we can start.
Okay, so let me share my screen. Can you see the presentation now?
Yes.
Okay, perfect.
Yes.
So thank you everybody for coming and listening to my talk about my story at PySchool and afterwards, I suppose. So I would say let's dive right in. So as Cristiano already mentioned, I am a PySchool of AI alum. I was part of the Spring 2023 session AI for Good Challenge, in particular for seasonal wildfire forecasting. And so this was a collaboration of the PySchool and the National Observatory of Athens. And we actually presented this twice. So once at the pitch day at PySchool, and then again at the ESA Phi Lab in Frascati. So at the bottom left, you can see almost the entire team. Only Cristiano is missing. So at the bottom left and right.
Maybe because I was taking the picture. One of the picture maybe was taken by me. That's why I miss.
I think this was actually at like some other conference where we happened to bump into each other in Vienna.
That one. Yes, I remember. That's
so on the left and right, you can see Johannes Papoutis and Johannes Pappos from the National Observatory of Athens, and in the middle there's Giovanni, the other fellow, and me. And then in the middle at the bottom, this was me at the PySchool pitch day, and on the right you can see me at the ESA Phi Lab in Frascati, just to show off that I was there. I guess I just wanted to include this picture. All right, so maybe a little bit more about the PySchool project. It was part of the Ceasefire Earth System Deep Learning for Seasonal Fire Forecasting in Europe, which was a 12-month project funded by the European Space Agency. And the background is like for a lot of things in Earth observation right now, climate change is kind of changing what we knew quite a bit. So in terms of wildfire, there's these days a lot of mega fires that go out of control, and that is at least in some part due to climate change. So we need to kind of anticipate the fire danger and understand the driving mechanisms on a global scale to be better prepared to respond to wildfires. However, wildfires are super complex processes, and they depend on many complex interactions between weather and vegetation. And these mechanisms also differ depending on the region and time scale. So as you can imagine, for example, a fire in a eucalyptus forest in Australia is very different from a fire in a boreal forest in Canada. And the Ceasefire project just aimed to address this challenge by using and leveraging Earth observation data So the National Observatory of Athens has collected a really big amount of fire driver data, such as like climate data, vegetation data, population density, and so on and so forth. And also some wildfire-related data, like, for example, burned area over the course of 20 years. And you can see some of the variables and how they change throughout a year, on the right-hand side. And for the PySchool project, we used this data to train some machine learning models and gain some insights into regional fire drivers. So like what causes or influences wildfires depending on the region. And if you're interested in this, I think the video of the pitch day is still available, and you can reach out to me as well, and probably also to Cristiano, and we can definitely provide more info. And yeah, so much for the PySchool project. And these days I am working for Aurora, which is also in the Earth observation sector. We are a company that was founded in Munich in 2018 as a spin-off of the Technical University. And we build satellites with thermal infrared cameras to detect wildfires from space. And the data that is gathered by our satellites, we then use and process to help our customers with the early detection of wildfires, to make better informed decisions on how to battle and prevent and respond to wildfires all over the world. We are currently approximately, I think, 120 employees in Europe, North America, South America, Australia officially, but honestly, we're pretty much global, as a lot of my colleagues are traveling all over the world all the time, for example, also to Asia, to talk with customers and help and support. We currently have around 300 users in 20 countries and 2 satellites in orbit. Here's some more stats. So we have more than 300 million hectares of total area monitored for our customers, and more than 116 million hectares of forest protected. So what you can see here is, maybe it looks a little bit complicated, but I can go over it a little bit. So here you can see the hours of the day, so between midnight and then midnight again of the next day. And here in gray, you can see when and what time of the day satellites are passing. So there's some that are passing in the night, some that are passing in the morning, and then some that are passing again in the late evening hours. But the problem is that the peak burn period, so when the wildfires are most active, is in the afternoon, and this is where there's currently no satellite coverage. And this is where our Aurora satellites are coming in. So currently we have 2 orbits in space, 2 satellites in space, and we are already covering sometime in the very early morning and sometime in the early afternoon. But we just prepared for the first plane of 8 satellites, and the satellites are already done and just awaiting launch with SpaceX. So by the end of this year or early next year, we will have 8 satellites in space, and in another 2 years or so, we will have our full constellation of 100 satellites, which will then give us a 30-minute revisit rate, meaning that one of our, every 30 minutes anywhere on Earth, one of our satellites will pass and take a picture and be able to detect wildfires in that picture. So these are a little bit more technical details. So today, with our 2 satellites in space, we have currently a revisit of 24 hours, so once a day. And the latency, meaning how long it takes for the detections to go down to space, from space to Earth, is about 8 hours. And currently we have to task the satellite, meaning that we have to specifically book that a satellite will take a picture of a certain area. But with the plane launch, we will just systematically take pictures like all the time pretty much with a 410 kilometer swath. And that means that like the satellite can see a 410 kilometers window. And the GSD, which is the ground sample distance or like resolution, is natively 200 meters. And we can improve this with super resolution, but I will go into this into more detail in a little bit. And with the plane of like several satellites in space, we will then achieve a latency of only several minutes. So it will only take a couple of minutes from detection to notification on Earth. And actually, I wanted to mention this briefly, that last week we signed a contract with the government of Greece. So Greece will become the first country to implement a national wildfire monitoring system using our thermal satellite technology. And we will then provide real-time fire alerts to the Greek emergency services. And it's a project that is led by the Greek Ministry of Digital Governance, the Hellenic Space Center, and the European Space Agency. And it's actually a full circle moment because the National Technical University of Athens will develop the data product algorithms. So Johanna Strebl and Johanna Strebl from slide 2 will again be involved in this project now. So as you can see, the wildfire community is relatively small, but yeah, also very nice. All right, then let's maybe talk a little bit about what our AurораTech satellites can do and see. So the cameras of our satellites are detecting light in different spectral bands. So light in different wavelength ranges. And for the satellites of AurораTech specifically, we detect different ranges in the infrared spectrum. And infrared waves or infrared light are part of the electromagnetic spectrum, and the human eye cannot see it, but humans can also detect it as heat. And the cameras detect this, and this is why they are so suitable for detecting wildfires from space. So just like how optical cameras kind of detect green, red, and blue channels, the thermal satellites use different infrared channels to capture temperature data from Earth. And for AurораTech, we have sensors in the mid-wave infrared and long-wave infrared channels, and they're both designed to detect heat, and yes, why we can like kind of capture temperature changes in like on the Earth's atmosphere, so to say. And we can also thereby like kind of monitor changes that are not visible to the naked eye or in the visible spectrum, such as heat of wildfires, for example, through clouds or smoke. I think that's probably it, because we don't have a lot of time, but if there are questions later, I would be happy to answer them. So here are just some examples to illustrate this a little bit better. So here you can see an example of a bushfire in Australia in October 2023 and how it looked like in the long-wave infrared spectrum. So the colors represent the different temperature ranges. So hotter areas are brighter and cooler areas are darker. And the long-wave infrared can detect varying temperatures within a fire and can also kind of help understand the fire's intensity. And what else? Now maybe as a comparison, this is how the same fire looks in mid-wave infrared. It's another type of infrared, and it can detect intense heat, especially then something like flames and high temperature sources. And it's particularly useful for capturing the extreme temperatures emitted by active flames. And you can see this quite well. You can kind of see the active areas of the fire. So you can kind of pinpoint the exact location of the hotspots, and this is really essential for accurate and efficient, like firefighting, for example. We are, however, not just active in the wildfire sector. We also do other things with our satellite. So wildfire detection, as I already said. But we can also, for example, track urban heat and land surface temperature. So on this slide, you can see the city of Los Angeles and the mountains and desert beyond. And you can really see the contrast in temperatures here between like kind of urban areas and natural landscapes. So you can see that within the city, it's really, really hot. And then in the mountains and then the deserts, it's kind of cooler. And this is also known as the urban heat island effect. And this kind of happens because cities have more concrete and more like paved areas, and they retain heat much better or like much longer than, for example, natural areas and trees, which would kind of cool the surroundings. And this is really important because extreme temperatures can really affect human health and energy consumption and infrastructure in cities, and can then help facilitate better urban planning, like, for example, the placement of green spaces, cooling centers, or also just heat mitigation strategies in like vulnerable areas of cities. The same is true for sea surface temperature. With our satellites, we can also determine the temperature of like water surfaces. And it's really kind of crucial in understanding, for example, ocean dynamics and how oceans and other like currents and other water bodies kind of interact with one another. And on the left-hand side, you can see comparison between a satellite image in the visual spectrum and kind of a thermal map. And you can see here that the water is a lot cooler than like the land, and the very dark here are some clouds that are cooler than the surroundings. And most importantly, you can see here like some ocean current that is kind of spinning, and this is only visible in the thermal spectral band, but not in the visual. And this just helps scientists understand with the like dynamics of like coastal ecosystems and like water bodies, and it's really crucial for studying biodiversity, fishery management, and also climate change impacts on the region. All right. This was more of like a physics-based product. Now more into the like machine learning and AI field, I want to say. So our satellites also use on-orbit processing to handle data directly in space, and thereby we can really speed up the entire process of detecting events like wildfires. And we can really reduce the time to process and analyze the data before sending the data to back to Earth, because this is often a large bottleneck in satellite data. So how this works is that the raw like thermal infrared data is collected by the satellite as it orbits the Earth. And like instead of sending the entire large raw data to Earth for processing, the satellite uses onboard algorithms to do the processing in space. So this reduces then the data size that is downlink significantly and can enable much, much faster notification because, if you'd only have to send a couple of, like, say, megabytes instead of gigabytes, you can really reduce the downlink time and thereby also the notification time for critical events. And this then allows for much, much faster responses to wildfires on ground. And this is really, really important for our customers in emergencies. So with the on-Earth processing, on-orbit processing, we can really streamline the communication process and ensure that our data can be sent to our customers as quickly as possible. Here's just a graph that shows how fast we will be able to deliver insights to our customers with the plane of satellites compared to other currently available satellites. All right. So much for the theory. Let's now maybe look at the Aurora Tech data products in a little bit more detail. So we have a bunch of data products that are, like, a bunch of them are already live and available to our customers, but we are also doing a lot of research and a lot of kind of proof of concepts, and I want to show you some of them. So maybe a little bit more regarding to the land surface temperature and what differentiates the Aurora Tech land surface temperature product from other products. So when we talk about land surface temperature, we are talking about high frequency land surface temperature that allow us to track really temperature changes on the Earth's surface. So current satellite technologies kind of have really a trade-off between, like, daily measurements with low resolution data or, like, for example, weekly measurements but high resolution data. But with our constellation, we aim to deliver sub-daily measurements at a 200-meter native resolution. But it does not stop there, as you can see here. We also offer super resolution, and the super resolution technology uses AI to shorten the satellite data and we can thereby increase the native resolution by up to 4x. So I think the goal was to then go from the 200 meters resolution to, I believe, of 50 meters resolution at an accuracy of approximately 2 Kelvin. And with this level of detail, we can we hope to uncover previously unseen dynamic land processes such as temperature changes in forestry and agriculture and also urban environments, for example, for irrigation management. But also for wildfire risk management, the increased clarity and frequent updates will hopefully allow us for faster and more accurate intervention. And other fields for application are, again, urban planning, for example. And our research has also been presented at, I think, several conferences at this point, and we've shown that our super resolved data from the Forest 2 land surface temperature can outperform existing products such as the NOAA from the, I think, NOAA 20 VAERS, which is, I believe, from NASA, with accuracy improvements in regions like East Africa, for example. Then we also provide an active fire near real time data product, and this again references the onboard processing and low latency downlink that I talked about earlier. so we can detect and monitor fires in near real time. So the latency will be achieved by, as I said, on-orbit processing, but also by an inter-satellite communication. So we will be able to kind of send back and forth data between the satellites and then downlink to the closest ground station on Earth. And this will also help in closing the afternoon gap because, as I think I'm repeating myself a little bit, but it's a really cool thing, so I don't mind talking about it more than once, with the revisit rate of 12 hours next year and 30 minutes in 2 or 3 years. We will close the afternoon gap quite significantly, and will offer faster and more detailed fire detection solutions than current alternatives. And we hope that we can help our customers improve their firefighting responses and wildfire management with that. So what we are currently doing while we are waiting for our first plane to launch is the OT active fire aggregation. And you can see a visualization of some wildfires in Canada and how they evolved. And so in our current solution, we use more than 20 different satellite sensors and integrate the data from them to detect and monitor and track wildfires. And so far from our customers, we've received really good feedback that our solution has really unmatched accuracy. And as far as I'm aware, there are also we are the kind of wildfire solution with the most satellite data. We have data, or we are using satellites in low Earth orbit, which kind of circle around the Earth and are usually, so they're closer, so you usually have a higher resolution, but you can only take a picture when the satellite passes. But to make up for this, we also have satellites, or are using data from satellites in geosynchronous orbit, so they are always at the same position relative to Earth. So they are, so with them, you can somehow get a continuous coverage. However, you usually have a lower spatial resolution, but we also use AI to kind of integrate the data and filter out false positives and make all of this available in our wildfire solution, where you can also then see some contextual metadata, such as the wind, the weather, the land cover, meaning like what's growing there, lightning strikes, to make more informed decisions on what to do with wildfires in your area. All right. So this was now mostly work that my awesome colleagues have done so far. So maybe now a little bit on what I am currently working on. I'm working on the fire spread model, and I believe some of my colleagues from my team are also here today. So for the fire spread prediction, we take into account multiple data sources to kind of create a prediction of how likely a fire will likely spread over the next. Per default, we say 12 hours, but it's also possible to request it for, say, for example, 24 hours. So the data that we use is DEM, which stands for Digital Elevation Models. So they provide information on the terrain, so like slopes and elevation. And this is really a key factor in determining how quickly and in which direction the fire will spread. For example, if a fire is moving up a slope, like up a hill, it will move faster than downhill, because if it burns uphill, there will already be like heat kind of rises, so the heat of the burning fire will already preheat the like trees and plants that are there, so it's like more likely, or like they will then like catch fire more easily than downhill, for example. We also use land cover, so the vegetation coverage. Understanding the type of vegetation that's like involved in a fire is also very crucial, because different types of plants burn at different rates, and this really affects the fire intensity and spread. This is also probably kind of obvious when you think about it, that like some grass will probably start burning really, really easily, but it won't burn really hot and for a long time. But for like trees, it's kind of the opposite. They will not catch fire so lightly, but once they will burn with a high intensity for a long time. And we also use the active fire data that I just talked about to kind of know where to start the model. So we continuously detect the active fire locations, and we thereby can ensure that we always use the latest available, most up-to-date information. So once you've gathered all these inputs, we generate fire predictions, or like fire spread predictions, for the next couple of hours. And helping our customers and emergency responders better anticipate the fire's movement and make better decisions on like where to attack a fire, or whether or not to evacuate the city, for example. So this is how it looks like in our wildfire solution. So the kind of gray area here is the wildfire cluster, and the little fires are the hotspots that have been detected by the satellites and that have been clustered. And the colors kind of represent the hours. So the fire, according to our prediction here, will be around here for the first hour, second hour, third hour, fourth hour, fifth hour, and so on and so forth. And then, as I said, we also enable like overlays with some metadata. So here, for example, you can see the wind, and wind is also a really, really important factor in fire spread, because the direction and also the speed of the wind is really, really influential for the path of the fire. So higher wind speeds obviously make the fire move a lot faster. It also provides more oxygen, so it can burn hotter. And something that is maybe not super obvious is that very high wind speeds can also carry flying embers further, and like start a wildfire somewhere that's even like a little bit further away from the original fire. I think about the fuel types I already talked in some detail, but here you can also see a visualization of that. So this fire is burning mostly in grassland, a little bit of forest involved, and like some bare areas. So this is most likely then a fire that's like not super hot and probably only burning for a short time, because grass doesn't provide as much fuel as other types of vegetation. And maybe a little bit more about the data product itself. So there are also other solutions out there that do that also predict fire spread. However, the Orotech fire spread offers really, really a fast propagation prediction given compared to other solutions. And we also combine data from satellite observation with physical fire models to really offer like a near real-time automatic fire spread prediction without much like user intervention. So in our system, you can just click a button, predict fire spread, and it will predict how the fire will spread, whereas other solutions require much more fire expertise, and you have to like manually insert a lot of physical combustion parameters, for example. Here I brought a little demo of to show you that our model really works, so to say. This is a screenshot or a GIF of the Aurora Tech wildfire solution and of the one of the very, very large wildfires in Greece last year. And this was in gray here with the blue outline. You can see the hotspots and like wildfire cluster on the 18th of July at around 2 a.m. and the 12-hour prediction. And then maybe a little bit hard to see in blue, and you can see the fire hotspots 12 hours later.
So, Johanna, sorry, I didn't get, these are the prediction or are this simulation is about the prediction of the model?
Yeah, so the blue, the colorful ones are our prediction, and the blue red ones are the actual detections. And you can see that there's a really high overlap, and our customers or like partners in Greece were like really glad to be able to like have this information to better kind of attack and fight these fires. But I'll be quick. I think we don't have a lot of time left. Then we also have a burned area product. So the satellite data with the hotspots can only kind of approximate where fires are because we detect the heat. And obviously a fire is hot, not just where it burns, but also a little bit around it. And from like before and after pictures, for example, in the visual spectrum, we can then also use AI to see the like really burn scars of a fire. And you can see on the right hand side here the actual burned area, and in blue around the fire hotspots. So you can see the hotspots are a little bit bigger than the burned area, but in general they correspond quite well. And the hotspots are also a really good way of like approximating the fire in real time, because like the satellite data of the like heat sources we can have in real time or near real time, but for the burnt area we really need those before and after pictures, and it really has usually has a latency of a couple of days. So if you want these real-time insights and really make kind of informed decisions on what to do now, you need to use the hotspots. But if you want to have some insights after the fire, for example, on like calculating your losses, if you own, for example, a large forest, then this can maybe burnt area is a better option. And then we are also doing some research on short-term fire hazard prediction. We started doing this because we now have really like a kind of best-in-class extensive archive of really petabytes of global wildfire incidents data. And we did some data exploration, and we already saw that we can beat some conventional models because we can really learn from real-world fire events and kind of really also improve our models as we go, as we get more data. And we also have some research out on that, but currently no data product. I think sea surface temperature we already talked about. So I guess that's it. If you have questions, feel free to reach out to me. And if you are interested in working with us, we have a lot of positions open in Munich and then also in Athens. And if you're interested in working remotely, we also can make that happen. So if you're interested, just click on the link and apply.
So thank you so much. So first of all, before starting with the question, as soon as you know about some job position or some openings, you can share it with us, and then we can spread it in the alumni community. I'm sure that there are plenty of people interested in working in this field. And yeah, let's start. If you have any question, feel free to unmute yourself. And
I can stop sharing for a second so I can see if anybody has a question. As I said, you can also, of course, just shoot me an email, and I'd be happy to answer your question.
So hi, Johanna. I joined in a bit late. Yeah. So my question is, the data that you train your model on, how did you get that data, and what kind of models are you using for the predictions, or what was the choice of your models?
For like which one are you
building
referring
the predictions where you showed where the fire would go? Like what kind of models are you using for that?
So for that we use a physical model. It's the raw thermal model. It's one of the most commonly used models in wildfire management. But we have done some research on improving the parameters of the model with AI.
Okay.
I can maybe send a link to the model if people are interested in that. Let me just I think it's this paper, but I'm sure you can. Either it is this paper or you will find the original paper linked in.
Sure. Thank you so much.
Yeah.
So if there are other questions, feel free. In the meantime, I have one very simple question. I'm curious about your satellites. So you told us that now there are 2 of them, and they will be 8 in the next year. So just to understand, because I'm not an expert of satellites, but I'm curious how big they are. Where was Aurora Tech to build them, or there are companies that you can ask for to build them? So how does it work?
Yeah, that's a great question.
It's not your. I know it's not your expertise, because you are a deep learning scientist, AI scientist. But maybe being there, you heard about it. I don't know.
Yeah, so we actually built the satellites in our office in Munich. We have some labs there. So I think for the first satellite, maybe also for the second, we only built the payload, so like the camera and the sensor ourselves, and the kind of ecosystem and the box that everything is in was provided by some other company. And the size is like approximately of a shoebox. So maybe a box for boots, maybe not for small shoes. And but for our latest satellite, my colleagues actually built the entire thing. So not just the sensors, but also the body and also the like operating system and everything that, like all the components pretty much. And we kind of built a satellite, and then it needs to undergo a lot of testing. For example, a shaker test, if it can like withstand all the movement during the launch, and also radiation test, if it can withstand the radiation in space. And once it passes out of this, it goes to our launch provider, which is like kind of a larger box where many of the small satellites are in. And this then goes into actually a SpaceX rocket that will be launched. And then once it's in the correct altitude, will kind of just push the satellites up.
Yeah, this is super interesting.
So we also have more hardware-focused positions if anybody is interested in that.
Yeah, that's super cool. So congratulations.
Thank you.
So if there are no other questions, I think we can quit. It was super interesting. And again, if there are questions, please interrupt me. Feel free to interrupt me. So again, it was super interesting from my point of view. And thank you again, Johanna, and let's stay in touch. Tell us as soon as you drop the other satellites in the space. We will be curious, and let's keep in touch for the job position. And for everybody, I just want to add that today PySchool launched, together with the European Space Agency, the collaborative innovation network. You can check on our social media. That basically is a network that tries to mingle together, to entangle together people that are experts in emerging technologies like AI, quantum computing, high performance computing, quantum sensing. So emerging technology together with Earth observation experts. The idea of the European Space Agency is to build this network, and PySchool is helping in that, build this network of experts of this cool technology that might be applied to Earth observation and space. So please check PySchool social media and the last post where you can find any detail about this project, because from the next weeks we will share with you and with everybody basically some calls for collaborating with the European Space Agency on this topic. Obviously, if you are an expert of this kind of topic. And so that's all from my side. And thank you again, and hope to see you in the next Tech Talk.
Thank you. Have a good rest of your day, everybody.